how to compute the velocity, linear and angular velocity of a kinematic chain. This is just showing two links of the chain. We are interested in computing the velocity of the frame, so OI dot with respect to the world frame, and also its angular velocity, and also the linear velocity of the center of mass, and of course the tip. And so what I did was I took up the 3-link manipulator. This is a 3-link manipulator, and then I just do this calculations, which I basically took this equation, and then I just propagate this one, so this equation for the revolute joint, and I propagated it along the links, and I got a formulas for the velocity of the frame, v1 0, v2 0, v3 0, omega 1. I also got the velocity of the tip, which is the end effector, and then I think I also have velocity of COM somewhere. Yeah, there it is, the pink one. So velocity of COM. So what I'm going to do now is I'm going to show you that you can do the same thing. Just take this and convert that to a code. This will be my attempt to get the velocities, but then you also can check these velocities against what MuJoCo computes inside it. Okay, so let's call this inverse kinematic. Sorry, differential kinematics. My bad. Differential kinematics, and then within that I'll rename this as differential kinematics. Yeah, I don't need this hello.xml nor this template. Okay, so let me open this file in I open this in Visual Studio Code, and then if I run this, it will basically do the forward kinematics. See what it gives. Okay, so this is just some configuration I chose. Quit this. Just to make it quit really quickly, let's say in 1 second. Okay, and then it essentially prints the end effector position, which MuJoCo thinks what it is, and then what I get from my calculation here. Only the XY is shown because it's a planar manipulator, so the Z doesn't really bother. So I'm just going to comment that out because this is not what I'm trying to do. I'm going to do the velocity part of it. So let's comment everything which does code this commented. Okay, now it's I can comment this out too. Okay, so now it's doing nothing but just doing the forward kinematics. Okay, there's another file I want to open, which is the XML. Now, in this case, when I'm trying to do the velocity, there are two things I need to supply. I need to supply the position configuration, which I already did. That is the data.qpose. The other thing I need is called data.qvel. That is the velocity. Now, one way of specifying the velocity is you just specify in this file, and then you can assign data.qvel to it. But you could also do it using the key. Remember, there was a key which is over here. You could specify another key for velocity, and I'm just going to just cook up some random numbers. We're going to check the calculations for these random generated numbers. Okay, so these are the velocities of the 3 links. We go back here, and then we access it the same way we accessed velocity. Qvel equals model dot qvel key. Now, this is something which you can get from the documentation, why it is model.qvel. That's how you get the velocity. So once we get that, I'm just going to copy it. Dot q equals q dot copy. And then now that I have the velocity and position set, I'm going to create my own function. Let's call it differential kinematics, with its input being the position. So forward kinematics, we only need the position, but for velocity, we need position, and we'll create u. I don't think I've defined them, so let me just define them here. So q equals data dot q pose copy. So this is just saving that, and qvel dot copy. Okay, so now it will go in this, and now what I'll do is this differential kinematics, I'll make it compute the velocities of the frames and the velocities of the COM, and of course the tip velocity. Okay, so that function is not defined. Let's go and define it here. From differential kinematics, import differential kinematics. Okay, so it's not available. Let's create a new Python file. New file, Python file. Save it as differential kinematics.py, and I think its the path is right. Okay, and if okay, now the inputs as said was q and u, and then I need to work on the details of this file. Okay, so what I'm going to do is I'm going to resort to what I wrote down in the equations, which was here. Let's start off with these equations. So the 0 indicates that the velocity of the world frame, right? The velocity of the world frame with respect to itself. The world frame is fixed; it doesn't move. So its velocity, angular velocity is 0, linear velocity is 0, and then this recursion basically tells us how to compute the velocity of the different frames. So going back by the figure, you see this frame here. The blue one is 0, so it does not move, so that's 0. And then I guess the purple one, which is attached at an angle, that is with respect to theta 1, that one will actually have its linear speed is going to be 0, clearly, because it's attached here, it's not going to move. But its angular speed is actually going to be theta 1 dot, as you can see. You don't need to do any calculation. So then I can calculate the linear and angular speed of this frame attached to 2, 3, and so on. So that's what this formula is. And I'm just going to take this formula and write it down in code, and then we'll see what we get. And then we'll, of course, compare with MuJoCo. Let's do that. Okay, so what do we need for the formula? Well, we need to specify this to be 0. This is the velocity of the world frame. I need to import P as NP. And then same thing for V. Okay, so that was easy. Let's move on to the next one. So next one is this formula. Omega 1, 1 is R10 transpose omega 0, 0 plus theta 1 dot k. So I'll write that down. Okay, so I need R0, 1. So this is 1 with respect to frame 0 dot transpose. I still have to define that. I've not defined it. Times W0, 0 plus, now it will be the first element U0 times the unit vector in the k direction, which I have not defined. Let me define that quickly. So k is np dot array 0, 0, 1. Okay, so I'm missing R01. How do I get R01? Well, I could figure that out, but actually I've done this work in the forward kinematics. So why don't I use it? So the forward kinematics, this is from a previous class. I had done this work of computing H01, which basically has R01, right? It's the first 3 rows, first and 3 columns, and so on and so forth over here. So why don't I just extract them out? So I'm going to just add to this, send H01, H01, H12, H12, H23, H23. So now it's available for use. So I go here and then I import. So from forward kinematics, import forward kinematics. Okay, now once we got that, we can now get the data. And remember, the inputs for the forward kinematics, it does not depend on the velocity, just the angles. So we have that. Now we need to get H01, which is just sol.H01. Okay, and then R01, let's just, we can define it right here. R01 will be H01, first 3 rows, first 3 columns. And I think all this should. So I'm just going to try to see if this works. Right now, I'm not returning anything. So we could maybe make it print. Missing one argument. Okay, so I'm missing one argument because that's not how forward kinematics is defined. If you look at forward kinematics, it needs Q and params. In fact, there actually is something I commented out, the usage of this. So if you go, okay, right here, that's how you comment. So what I'm going to do is, instead of trying to send it directly from there, let me just call this, send this from right from here, this file. Okay, so that's the parameters. I'll send the parameters right here. And then those will go to differential kinematics. And then they should go here. Okay, now I think it should work. Let's see if it works. Okay, there's another error. Okay, I think I made a mistake with the way I define array. Oh yeah, one extra R. Okay, so here it is. We have 0, 0.1. That's the angular velocity of the first link, θ1 dot, essentially that. Okay, so so this just says the code works. I'm just going to keep copying that and get everything up and running. And then I will not know if my answer is correct unless I check it myself, or I use MuJoCo to check my calculation. So this is angular speed. Let's look at the linear speed. It is R10 transpose everything here. So let's put that in the equation. P11 equals R01 at P00 plus, I think it's 00 cross with 010. Okay. 001. Okay, so I need to the cross product, and I could do the cross, but then I could use vector skew, which was something I did earlier. You could write the cross product with a skew symmetric matrix times a matrix. So let's do that. So I think it's defined in my utility. And the utility is, I think, missing here. Let's see. So I don't have the utility, so I'm just going to copy it from, I think I made a saved copy here. Let's get it from here. and use it. Got that. Now let's vec to skew. That'll be 0, 0. Okay, I still don't have O1. That is basically the uh, position of the frame, right? You can get from H01. It's basically the fourth column. So that's the fourth column. Okay, let's see if this part runs. Print V11. So it'll get a lot faster once I get one of them figured out, because then I'll just do copy paste. Okay, 0, 0. No wonder it's 0, 0, because it's attached to the world frame. Okay. Okay, so all we need to do now is just take this piece and then just keep copy pasting it. So for example, take this. This next we go to 1, 1, 2. Why is this happening? One, two, 2, 2, 2, 2, 1, 1, 1, 1, 1, 2, 1, 2. 1, 1, 1, 2, 1, and I don't think I have these. Okay, so I can get them from here. H12 is sol.h12. And then I need to do it once more. Then we have 2, 3, 3, 3, 3, 3, 3, 2, 2, 2, 2, 2. Okay, so okay, it's missing that, missing this. H23 is sol. Okay, so what I've achieved here is I've computed V11, W11, and so on, which is essentially the position of all these things have been achieved, but then they are all with respect to its own frame. We need to figure out what's the linear and angular velocity with respect to the world frame. So that can be done by using this formula. All I need to do is multiply R V11, pre-multiply with R10, and I get the velocity with respect to the world frame for all of them. So that is super straightforward. Let's do that. Okay, so last thing is W1. I'll ignore the 0, because when I don't put that 0, it means it's world frame, equals R101 times W11. W2 equals R, I need 0, 2, which don't have it, 2. W3 is R03, W33. Okay, copy paste. Same for velocity. It's V1, V2, V3. Okay, I need to get R02, R03. That's pretty straightforward. Let me, well, let me just define them here. So R02, R01 is already defined, is R01 times R12, and R03 is R02 times R23. Okay, so with this, I've essentially done with the linear angular velocity of the frames. Let's look at the center of mass. The center of mass formula is here. It's V1 plus omega 1 cross PC1, PC2, where PC1 is going to be the position of the center of mass of the first link with respect to frame 1, frame 2, and so on. What that means is if you go to this, it's going to be this position in this frame, in the purple frame. Then it's going to be velocity of the position of C2 in this frame. So you can see all those positions. For example, C1, it's along the x-axis of frame 1, x-axis of frame 2, and so on. Okay, so let me define the positions first. P C1, so that would be NP array. And I've defined it, I think it's half of the link 1 length. So 0, 0. And then PC2, PC3 will be 2, 3. Okay, now I'm ready to use the formula. It is here, V1, 1 plus cross product of omega 1, 1 PC1. So let's define as VC1 in frame 1 equals V11 plus vec to skew W11 times PC1. Okay, and then I just need to do the same thing for other frames. Three. Okay, so at this point, you're just computing the velocities in its own frame. Three, V2, 3, 2, and then okay. Now we have the velocity in its own frame, but we need to find the velocity in the world frame. So it's the same. It's the same thing as we did before. And I've written it down here. It's going to be this the rotation matrix times VC1, VC2, and so on. So let's take that and put it into action. VC1 equals R01 times VC1 score 1. Okay, that's that. We just have to copy it 2 more times. So 2, 3, 2, and then 3, 3, and I'm missing this. So 2 and 3. Okay. So the second part, which is the velocity of the center of mass, is done. The one more part left, which is I need to compute the velocity of the tip, the end effector. So for that, I need to use this formula. This is the last link, and you can see it's basically V33 plus omega 3 times position of the end effector times n, and then omega e is actually same as omega 3. So that is very straightforward. It's just going to be reusing one of these formulas. So take this, and I'm going to call this as the velocity of the end effector in frame 3. So V33, only thing changes here is that I need the position of the end effector. So let's call that E in frame 3. And the position of the end effector in frame 3, the way I defined it is it's going to be NP array L300. Okay, and then omega E in frame 3 is omega 33. And finally, to compute the world frame velocity, it's VE. It's simply R01 times PE3. And then WE is R03, my bad. 03 WE. Okay, I'm done with getting all this, but I need to pass them back to the main file. So what I'll do is I'll use the same trick I used before. I'm going to use namespace. Let's try to run this. Looks like you cannot detect something. Right. Okay. L1 is not defined. Okay, no problem. We can fix that. So we know that L1 is just like this. It's going to be exactly the same. So we go here and then. Okay, so L1 is fine. Let's see if it runs now. Okay, it ran fine, just that it did not output anything. So it works fine. Okay, I'm just going to pass that back and then we should be ready to go to the next step, which is confirm that our values are right. Okay, so the convention, the way I do this is using the solution, return solve, where I define it like this. So let's take it here and then ask ourselves, what do we need to be returned? We clearly don't need these things. And the other thing I would like to do is not repeat the output name. So here it is SOL, and then I also call another one over here as SOL. So if we can call it anything, it's a temporary variable, so we can just call it sol2, and then we'll return sol2. Now, what do we want to be returned? Well, clearly we want VE to be returned, WE to be returned. We also need to return VC1, VC2, VC3. This is the velocities of the center of mass. VC equals VC1, VC2 equals VC2, VC3 equals VC3. Okay, we also need to return the velocities of the frame. So that is here. It's W1, W2, W3, V1, V2, V3. So let's return those. W1 equals W2 equals W2, W3 equals W. Okay, I think I'm done. Now let's go back here and get the output and then print. So what I'll do is obviously send me output for all the frames and velocities, but I'm just going to check with MuJoCo one of those links. Let's just pick randomly link 2. Okay, link 2 is nothing's really special about link 2, just that. So I'm just going to check the frame velocity for link 2, CM velocity of link 2, and the tip velocity. Why I chose link 2 is because it's not the first link, so I know it's not going to be 0. I could use this, but then its velocity, well, I could use 3 or 2. Both of them are good choices. I just said to you go with 2. So let's just confirm 5 things. One is the linear and angular velocity of frame 2, the center of mass linear velocity, and then end effector velocity, which will be 2 numbers. So 5 numbers. So here I'm going to output them, and then I'll show you how to check them with MuJoCo. So print frame free lin ang. Well, so this will, I will just make it print sol dot v, I think it was v w3, the w frame 2, and then print sol dot v2. Okay, so that will print the linear and angular velocity of frame 2. Will make it print the COM of 2, COM to lin well. So that would be print sol.vc2 and then print end-effector lin angle. Okay, so print sol.ve or we first, and then okay, so it's just going to print a bunch of numbers. That's a problem. We have a problem here. So it printed the velocity of frame 2, so three numbers. It printed the linear velocity, but here's a problem. For the angular velocity, it actually printed a 3x3 matrix. It can't be that. There's something wrong here with our velocity. It's this. This is the wrong operation. So that one will actually do element-wise multiplication, while this will do the actual matrix multiplication. So let's just run this. Okay, it's better now. So we have three numbers for the linear angle velocity. Okay, so this is my calculation. This is what I derived. I think it's right, but the only way, one way to verify this is to actually pick the values from MuJoCo and see if MuJoCo also thinks that's the same value. So it's all there in MuJoCo, just that we need to expose it. Now, the way you can get this is to use by using sensors. So I'll show you what sensors can do. MuJoCo. XML. So we need to go to sensors here. Let's define somewhere here first. Okay, here it is. Actuators, sensors. Okay. Now, what MuJoCo does is it has a bunch of sensors, and this actually makes it so we're getting to the place where we can do control. And for control is based on actuators. We've not yet started looking at actuators, but we're going to now start looking at sensors. Actuators will come a little bit later once we do trajectory tracking. For sensors, there are a bunch of sensors in MuJoCo. Touch sensor is just if something is in contact or not. Accelerometer is going to be with the acceleration, so it's going to be the linear acceleration. Velocity meter will be the linear velocity, gyro, force, so on. Now, there's also things you can do with this. You can actually add noise to the sensors. That way, you can simulate a real system, and so on and so forth. So what we're going to do is, in order to get the velocity of the frame, there is this thing. It's called frame position. Well, not frame position, frame velocity. If you want a frame position, you use frame pose. But if you want the velocity, you use frame linvel. This gives you the velocity of the frame, angular velocity of the frame. We also need, well, in this actually can be used to find the, you can actually use the frame linvel to find the velocity of the center of mass. So let's see how that works. So here is the documentation for frame linvel. This one will, you can specify object type. So you can get, for example, the velocity of a site. So clearly, we can put it at the site and get the velocity of the site. We can also get the velocity of the body. This body command gives the velocity of the center of mass. And you can see this x body. That actually gives you the velocity of the frame. Okay, so everything we need is buried right here. So once we use frame linval, we'll be able to get the frame velocity, as well as the center of mass velocity, as well as the site velocity. A similar command exists for frame angular velocity. You can specify the type, and that will give us access to its velocity. So the way this is done is you need to go to the XML, which I opened here. In here, just after the body tag ends, you need to define sensor. Go to end sensor. Okay, now what you need to do is you need to specify, just like you specify other things here, frame lin val. Let's confirm the syntax. Okay. Object type. Okay, so remember that the object types was, in this case, body, X body, and site. So let's take body. This is the center of mass velocity. We want to specify uh, to which body. Now, there are so many bodies. There are 3 bodies, right? Each of those links is a body. So we need to specify which body it is. So that would be object name. And since I'm going to only focus on the second body, if you go up here, we have specified body 2 is the one whose velocity we want to compute. So we'll call it body 2. And then we'll give it a name. That way we can call it. So I will call it body 2 Linwell. So everything which is needed is here. We have, wait, I need to call it name. No, it's fine. So we give it a name. This is how we'll identify it. We give it object type. This is basically saying with which frame you want to compute the velocity. And then we need to specify the object name. We can do this for, I'm going to do this for the frame. So that will be that X body. It's for the same body too. But let's call this body frame to Linval. Okay, we want to compute the angular velocity. We'll call it angvel. So that remains the same. And then finally, we'll compute the velocity of the site. So I'll take these to copy it. Let's call this site or tip. I think you call it tip in this case, the end effector. Okay, I think the name is right here. Say site name tip. Okay. So this type is going to be site. And then this object name is going to be site. So tip, my bad. Tip is the name of what we want to access. Okay. Now that we have it all set, we need a way to call this. Now, the way this is called or accessed is, let's take, this is fine. Okay, so now this is where I'm going to compare. The values I get from my calculation should vary. Should check off with the value which I get from MuJoCo. So the way you get the sensor is data.sensor. Then I need to give its name. So in this case, I'm trying to compare the velocity of frame 2. That is the angular velocity of frame 2. So I've given it a distinct name. That name here is here, angvel. So let me take that here. And then I need to say data. That is the data coming from this particular ID. And then similarly, copy this. So I need the angular velocity. So, and then the lean velocity. Okay, let's just check this. So things printed here should match up with the things we get from MuJoCo. I think it's right here. Pi frame to lin angvel is this 2 values. And you can see they match up with exactly these 2 values for the same. So that's showing that our calculations did produce the same answer. We can do the same thing for the other 3 things. So we want to the center of mass velocity. So that would be okay. So data sensor body to Linval. I think that's what I called it. And then lastly, we want the tip velocity. So let's copy this. We call it the tip Linval angvel, and then tip Linval mg and effector. Okay, so let's run this, and then if everything's right, then we should have a perfect match of values. So wherever you start. So let's start with frame. So you can see the frame, we check that they match, these line matches with that line, this line matches with that line. Let's look at the center of mass velocity. So this is the center of mass velocity that I computed, matches with that with MuJoCo. And then if you go here to the end effector velocity, this is the value I get from my calculation, matches with the value from MuJoCo. So that's just showing that what calculations I have on paper matches the calculations I get from MuJoCo. So that's the verification. Now I just did this for just body 2, but you could just take this and do it for body 1 and body 3 and so on. Okay. Okay, so why are we doing all this? Well, it turns out that when you're doing any control, you would need to know velocities of center of mass, frames, and so on. And that's it. That's why we are doing it.